So at the end of the energy investment phase, we've got glucose being phosphorylated twice. We end up with these two 3-carbon molecules, DHAP and G3P. Now we're going to get our investment back. The first thing we do is we tear off some electrons. So we get on the electron bus to form NADH from NAD+. And all of these now have this this number 2 coefficient in front of them because we are using 2 molecules of G3P. So remember, G3P, we get 1 molecule directly from aldolase, and then isomerase can turn the DHAP from fructose 1,6-bisphosphate into another molecule of G3P. So we end up with 2 molecules of G3P. We just get there a little bit indirectly. So G3P is going to have have a phosphate group added to it to form 1,3-bisphosphoglycerate. That is catalyzed by triose phosphate dehydrogenase. Dehydrogenase is taking protons off. And then we take those phosphorylated intermediates, yes, phosphorylated intermediates, we're coming back to see them already, to add to 2 molecules of ADP, 1 molecule per molecule of 1,3-bisphosphoglycerate. Remember, this is because we have 2 molecules of G3P from the energy investment phase. So phosphoglycerokinase takes off a phosphate group from each molecule of 1,3-bisphosphoglycerate to form 3-phosphoglycerate. 3-phosphoglycerate is going to be isomerized to form 2-phosphoglycerate using an enzyme called phosphoglyceromutase. For those of you who are keeping count, that is our 8th enzyme in the process. 2-phosphoglycerate is going to be turned into phosphoenol pyruvate, a molecule that we abbreviate as PEP, which is appropriate because it's got a lot of potential energy to it. We lose some water there. That is catalyzed by an enzyme called enolase. And finally, in the last step of glycolysis, we take off that last phosphate group to form pyruvate. So that's what pyruvate looks like. And that's catalyzed by pyruvate kinase, our 10th enzyme in the process. Okay, so pyruvate is our ending point for glycolysis. And you can see we went from having carbon in glucose to being all this carbon that is. These carbons are very much oxidized. They're surrounded by oxygen. They have hardly any electron density at all to them. But we can still put pyruvate to use in the next few steps. So pyruvate gets oxidized. And the next thing that happens is we send it into the mitochondrion, we meaning eukaryotes, where it goes into the next part of the process, which is called the citric acid cycle. Sometimes it's called the Krebs cycle. Sometimes it's called the TCA cycle, or the tricarboxylic acid cycle, which is all very confusing. So I'll just use citric acid cycle or Krebs cycle. Anyway, we have to get into the mitochondrion in order to complete the oxidation of pyruvate. And this is going to happen in the presence of oxygen. The pyruvate's going to enter the mitochondrion, and the oxidation of glucose will be completed. So, in order to get to the citric acid cycle, we kind of have to pass the velvet rope into the mitochondrion. We have to get into the mitochondrion. So we have to take pyruvate and get it into the mitochondrion. So there's this sort of half step in between glycolysis and the citric acid cycle, which is called pyruvate oxidation. Sometimes it's called acetyl-CoA formation. One refers to what happens at the beginning, and one of those terms refers to what we end up with. So we need to convert pyruvate to acetyl-CoA, or acetyl coenzyme A. And this happens in 3 steps. So here's coenzyme A. We looked at coenzyme A really briefly when we talked about functional groups, because it's got this thiol group here. Shh, it's a thiol group. And you can see it kind of looks, there's a nitrogenous base, there's a 5-carbon sugar that's phosphorylated. So yeah, this is actually, coenzyme A is related to nitrogenous bases. There's a couple of phosphate groups, and then there's all of this organic nonsense. And then this thiol group. And this thiol group is actually where we hook what's left of pyruvate onto coenzyme A. Okay, so in order to pass into the mitochondrion, the first thing that's got to happen is pyruvate has to be transported across the outer membrane of the mitochondrion. And as it does so, it's going to lose this carboxylate ion. This carboxylate ion, which is the ionized form of a carboxyl group. C double bond O, O, where's the H? The H is in solution. And you can see, without too much imagination, that's just a molecule of CO2, carbon dioxide. That gas that you're breathing out right now. So we lose a molecule of carbon dioxide. That carbon is pretty much completely oxidized, hardly any electron density at all to speak of. So we can just go ahead and breathe that out. So we'll get rid of that. So now we're left with a 2-carbon molecule. We're going to pull some electrons off of that, put them on the electron bus, send them to electron camp. And then coenzyme A, that big nucleotide-looking thing, comes in. Because it's so big, we're just going to abbreviate it by just writing out its name, coenzyme A, or CoA. And we hook that onto what's left of our pyruvate molecule, which is an acetyl group. This is an acetyl group right here, connected via that thiol group, that sulfhydryl group, to coenzyme A, and that's our acetyl-CoA. And acetyl-CoA is what's going to go on to the citric acid cycle. So here we see the citric acid cycle, also called the Krebs cycle, completes the breakdown of pyruvate to CO2. So we've lost 1 molecule of carbon dioxide in the pyruvate oxidation. So 1/3 of the carbon dioxide that you breathe out comes from that step, the pyruvate oxidation. The other 2/3 of the carbon dioxide that you breathe out is coming from the Krebs cycle. Now, I still haven't told you where the oxygen that you're breathing in is going to go to. We're going to get to that. It happens at the end. In the citric acid cycle, we're going to continue to oxidize acetyl-CoA and get some more ATP, some more NADH, and another electron bus called FADH2 is going to be produced as well. And that's all what happens per turn. And remember, per pyruvate molecule, that's per pyruvate molecule, but remember from glycolysis, we got 2 pyruvate molecules. So per glucose, glucose molecule that we start off with, we get 2 ATP, 6 NADH, and 2 FADH2 per turn, or per glucose molecule. Okay? All right, so we had our pyruvate out in the cytosol. We took off a molecule of carbon dioxide. We stripped off some electrons, put them on the electron bus, send them to electron camp. We add in coenzyme A to form acetyl-CoA, and coenzyme A introduces that acetyl group into the citric acid cycle, and then it takes off. It bounces. It's out. Coenzyme A takes off again. But we're going to see coenzyme A again in the citric acid cycle. In the first half of the citric acid cycle, we lose 2 more molecules of carbon dioxide. So that's where the other 2/3 of the carbon dioxide that you breathe come from, the first half of the citric acid cycle. We're going to harvest more electrons, put them on the electron bus, send them to electron camp. We're going to produce 1 molecule of ATP by substrate level phosphorylation. We're also going to produce a molecule of FADH2 from FAD, which is another electron bus. The electrons that go on to FAD have a little bit less potential energy. But that's what we get from the citric acid cycle. So the citric acid cycle also has several steps catalyzed by different enzymes. And the first thing that happens, the way it all starts, the cycle starts, is when we take that acetyl group, what's left of pyruvate that was joined onto acetyl-CoA, which is combined with oxaloacetate, forming citrate. And citrate is just the ionized form of citric acid. Citric acid, citrate, essentially the same thing. So eventually we're going to end up with oxaloacetate again, and that's what makes it a cycle. And it's these electron buses, NADH and FADH2, that are going to take those electrons away and take them to electron camp.